Hello and welcome to the final run of the full world model. Indeed, we're done with the 10 steps here. Congratulations again, because some of them were really advanced. And now that we did this, I'm gonna show you the full code, which is composed of what we implemented together and also some additional methods and functions to connect the full world model to the car racing environment, which of course we didn't implement together because this is mostly related to the car racing environment. And then of course, we will install everything, all the packages that we need to run the full world model, and we will do the final race. So we will do that in 3 steps, 1 step for each tutorial. The first tutorial will be about me showing you around the full code, both the inference code and the training code in the 2 separate inference and training folders. Then in the tutorial after that, we will install all the packages. And then, of course, in the 3rd tutorial, the very last tutorial of this course, we will do the final race. And you will do it with me. You will actually have the challenge to not only beat the AI, but also beat myself. And I practiced a lot. You're going to see that I will probably do better than at the very beginning of this course, remember in the first tutorial. So, double challenge for you. And whatever the result, for sure, you will have fun. Alright, so now let me show you around the whole code. So I've prepared everything from scratch, in Spider Anaconda, and right now only the temporary Python file is open, but we're going to close that soon. And in my desktop folder, I have the whole AI Masterclass folder of the course. So if I click on it, I will find the 2 subfolders, inference and training. You will get exactly the same. I will provide this whole folder composed of these 2 subfolders with all the codes in the very last tutorial of the course in an article. And so first of all here, let's see what we have in the inference folder. So in the inference folder, we have 4 Python files. The first one is, of course, the environment, and that's now, I'm going to close temp.py, here it is. That's the first Python file, and it contains basically the car racing environment in which we will do that final race. And not only it contains it, but also it contains some code here so that we can play ourselves, because it's not only us watching the AI race, it's also us playing against the AI, because we will also do the race, in 30 seconds, also corresponding to 900 steps. And so these are all the commands, basically, with left, right, up, or down, so that we can play it as well. Remember, the AI will play first, and then it will be our turn. So, of course, no need to implement that together. This is only related to the game. Then we have, of course, I'm going to show you in the right order, of the full world model process. First, the VAE. The VAE.py, so now you're going to recognize the code we implemented together, because indeed this is what we implemented together with, the convAE class, and inside, of course, the init method where we define all the parameters and variables of the CNN VAE, and then, of course, the build graph method, where we first built the architecture of the VAE composed of 3 main parts. First, the encoder, second, the variational part of the VAE, and third, the decoded part of the VAE. And then remember, we have all the training operations. But then we have some additional methods which are only used to basically connect the VAE to the car racing game. So we didn't really have to implement that together. That's not that important. The most important for you to understand about the convAE is really that part, with the full architecture of the VAE, which we followed from the article, remember. And then, of course, the training operations, which you're going to see in that second subfolder of the training. All right, so that's for the VAE. And now, the next part of the process, remember, is the RNN. So if we click on it, again, you're going to recognize what we implemented together in step 8. And so again, we have our MDN RNN class, which we built together, composed of 2 main methods. The init method containing all the parameters and variables of the MDN RNN class, and then again the build model method, which is structured in 3 main parts again. First, building the RNN, so that's where we built all the architecture of the RNN with, the LSTM cell, then all the dropouts, and then all the formations of the inputs, outputs, and targets. And then, of course, we have the MDN, mixture density network. So here we build the MDN, and also we get the MDN parameters, and finally all the training operations with that special loss function which we implemented from scratch in several steps, and the optimizer, and of course how we apply the optimizer to compute the gradients in order to optimize that loss error between the predictions and the targets. Alright, so that's for the RNN, and again you have some additional methods which are most of them used to work with the environment. However, this one is important. That's where we're going to load the weights, the pre-trained weights of the full world model, which are contained in this weights folder. So if you want to learn how to load some weights and save some weights with that second function, save JSON, into some JSON files, well, you have the functions as well. But no worries if we did not implement these methods together, because I provided all the comments for each and every method and code section of the full world model code. So for all of them, you will clearly understand what they do. See, for example, then we have all the hyperparameters, which, by the way, we saw when, we were playing with the hyperparameters and the RNN values Python file to understand what shapes we're building and what shapes are changing after our reshapes by the reshape function. So here they are again, you can play with them again, and then, we just create the object of the RNN. That's the hyperparameter HPS object, which we saw many times. Here we make this additional function that samples sequences of inputs for the RNN model using a pre-trained VAE model. So that's also kind of important, because you're going to see that when I'm going to show you the training, the training of the full world model happens in 5 big steps. And it's not only about training each of the components of the full world model, such as the VAE and the MDN RNN, it's also about generating some data, some sampled sequences of inputs for these models. But of course, that implies working with the car racing game environment. That's not something that you always have to do. Then, finally, we have the final full world model, which basically is the Python file which we will run to start the race, with therefore first the AI playing and then us playing, but on the same number of steps, meaning on the same amount of time, 30 seconds, and we will see at the end who gets the best score. And so here, what do? Well, basically we assemble everything, we assemble the whole full world model within a class, this model class. So you will recognize here all the objects of the classes that we built together, such as, for example, first, the VAE, right? This is an object variable self.vae created as an object of the countVAE class. Then same, we build a second object variable of the model class created as an object of the MDN RNN class, which we build together. And then, we set the parameters like the input size, the Z size, remember that Z size of 32, and some more parameters. And then some extra functions, again, mostly related to how we work with the car racing environment. So this is all customized to that, and therefore you don't need to spend too much of your energy trying to understand everything, because this is very specific. But there we go, you have all the code that will run basically that simulation, in this whole simulate function. And then here you go with the artificial intelligence result, which will be compared to the human intelligence result at the end. And I can already tell you that in order to beat the AI, you will have to do at least better than 900 points. And then, here we go, back to the main function, the last one, which will run the whole process. So P1 is the first process of the AI playing the game. And then here will come P2, meaning us, humans, who will start racing as well. All right, so that's for the first inference folder. And now let me show you the second folder, the training folder, which you will see is pretty big, and that's because you understand that we have to train every single component of the full world model. But not only that, not only we have to train all of them separately, but also we have to generate some data, as I told you, for each of the models. And that's why here in the training folder, I provided this Python file training process, which is only a bunch of comments, but which will tell you exactly what is the process, what is the training process to train the full world model. And so what this means is that if you want to train the full world model, but I will insist on saying that you will actually need a lot of patience and a lot of space on your computer, but I will say a few words on that later. But if you want to train, if you want to take the challenge of training the full world model, Well, these are the steps that you have to follow, meaning these are the Python files that you need to execute one after the other in that same order. So, well, let's have a look at them. The first one is env.py, which is the same env.py here that we have in the inference folder. So that's exactly the same, but you have to execute it as the first step of the training process. Then the next step is to generate some VAE data. And here we go. If you want to take the challenge to train the full world model to get your own weight, well, make sure to know that you will need a couple of terabytes on your machine, because in order to generate the VAE data, you will need to generate basically a lot of images, which therefore will take a lot of space. And that's not only single images, that's images of a game. So you will need for sure a couple of terabytes of free space. But once again, you're not supposed to train the full world model in this course. The full world model is usually trained on servers with high amount of space and also highly powerful computers. So just wanted to clarify this, but well, this is the second step, to generate some VAE data, and that you do with the extract.py file. So you just have to run this. Then let's see. The third step of the training is to train the VAE. Well, that's because since you generated some VAE data, now you have some data on which you can train the VAE, and that you do with the VAE train.py file. And of course, since you train the VAE on terabytes of data, well, that's going to take already some good amount of time, but that's not the worst. The highest amount of time that is going to be taken will be for the training of the controller inside the full world model. The training of the VAE and RNN will take time, but most of the training time will come from the training of the controller, which happens in train.py. But we're not there yet. The next step of the training process then will be to, well, this time generate some RNN data, and that you will do it with series.py, so this Python file here. And then, well, once you have some RNN data to train the RNN, well, naturally the next step will be to train the RNN, and which you will do with RNN train.py. This will again take quite some time, but that's not the worst. The worst is coming now, well, because the next step is to train finally the full world model. And by the full world model, I mean the controller. If you want, you can replace full world model here by controller, but basically that's the heart of the full world model, because that's the part that plays the actions when returning some well pre-processed inputs, including the time-related dependencies coming from both the VAE and the RNN. Alright, and so this will take days or even weeks on normal computers. I could even say 1 month. I haven't done it myself, but that's what I've been told by some people I know who work in the research field. And then finally, well, that's not part of the training, but of course, after training such a huge model, well, you will definitely want to run the model with your own weights, and that you do with the model.py file, which is exactly the same as this one full world model, but I just named them differently because indeed that full world model that we have here in the inference folder is linked to the best weights coming from the training of the full world model by the author. Here are the weights, controller weights, RNN weights, and VAE weights. You have all the weights of all the pre-trained models of the full world model, including the controller, RNN, and VAE. And speaking of these weights, well, they are by far the best weights obtained for that full world model, and we have exactly the score for these weights. That's what we see in the article of the full world model. And by the way, here you can see that the number of parameters, I forgot to show you this, is indeed less than 1000. So remember, the most appropriate evolution strategy is indeed the covariance matrix adaptation evolution strategy. But what I wanted to show you is, the results we get with the weights we use for our full world model, the ones you'll get in the folder. Well, these are the scores at car racing from different models, including the previous state-of-the-art AI models such as the A3C, the best AI model built on, the OpenAI gym competitions. And this guy, you will find him very easily in the leaderboard because he was the one to publish the previous highest score in most of the games like Doom, car racing, or even other Mujoko games. And his score for the car racing game was around 838. That was the best score for that game. But then David Ha and Jürgen Schmiedhuber trained their full world model and obtained the amazing score of 906. And that's the score you'll have to beat if you want to honor human intelligence. So you will see that when we start the race in 2 tutorials, well, the AI will probably do something around 906. And so good luck to beat that. All right, now what else did I want to show you? Well, okay, we're done with the full process of the training, so you can check this out if you want, the different codes. Again, everything is commented, all the code sections and also all the methods in the different classes. Well, here we don't have classes, but we have some functions, and for each of the function I clearly explained what they do, like for example this one, which returns the number of generated data files. Each file represents one game, one game played by the agent. Then this function creates a data set from the saved generated files and returns data, which will be the input of the VAE. So I try to be as clear as possible in my comments, but again, I want to give all the credit to the author. This is not my code, this is the code of the original developer of the full world model, David Ha, and also Jürgen Schmidhuber. So the original code comes from them, but as I told you, I restructured everything and I commented every single section of the code so that you can at least understand what's happening. But of course, the full world model is something between 2,000 and 3,000 lines of code, so we would definitely not implement all that together. I kept for you the important part, which is what we implemented together. Alright, so there is one last thing I wanted to show you in this training folder before we move on to, all the installations, and then finally, I'm so excited about that, the final race. And this last thing I wanted to show you, and I mentioned it before, I told you I would show you how to do this, is how to connect the different optimizers to the full world model. How to choose an optimizer coming from the master toolkit, which you will find actually right here, es.py, which we saw in step 10. So remember, in es.py you have all the optimizers, including the SGD based optimizers like the Momentum SGD or even Atom, and then you have all the evolution strategies that we saw one by one in step 10. So quickly reminder, you have the CMAES, you have the simple genetic algorithms, you also have the OpenES evolution strategy, and also finally the PEPG1. So you have all of them in evolution strategy, but you're not going to connect one of them to the full world model in this code. You're going to do that here in train.py, which trains the controller and which will take the largest amount of time. Well, as you can see in this train.py file, you have a couple of parameters here. You can select at the beginning and also at the end. In the argument parser class, you have all the parameters that you're going to choose to train the controller. And as you can see, one of them is the optimizer. And here you have all the options you can choose as the optimizer to train the controller of the full world model. And you will recognize them. You have, well, first the simple evolution strategy, then PEPG, the OpenAI evolution strategy, genetic algorithms, and the CMA. And as I told you, we're training our full world model with the CMA because, as we've just seen, the total number of parameters in the controller is less than 1000, so the CMA evolution strategy is the most appropriate, and that's why by default we selected that CMA as well as the value of the optimizer parameter here. But if you want to try another one, like for example the PEPG, which is another good option, but remember it's more appropriate when you have many more parameters, like thousands of them. Well, what you would do is replace CMA here by PEPG as well as above right here. And that's only what you need to do to connect another optimizer to train the controller of the full world model. Alright, so now we're going to move on to the full installation of all the packages that we'll need to run the full world model, in inference mode. I remind that we're only going to run the full world model in the inference mode and not the training because, as I told you, I don't even have enough space or enough power to train this. So for sure, no training will happen in this course, but we will definitely run this in inference mode to, race the AI. So I can't wait to do this together with you. Be prepared, there's going to be some challenge. Remember, a double challenge, so be ready for the show. And until then, enjoy AI.